Good morning, students. In the previous lecture, we studied about the valve timing diagrams for both your petrol engine. This is your actual valve timing diagram for the petrol engine. And we studied the valve timing diagram for the actual diesel engine. In today's lecture, we will start with the pressure versus crank angle diagram for we will take for the first we will take the 4-stroke petrol engine. Okay. Now in this diagram, uh, this graph is plotted between the pressure in terms of bar. The pressure is along the y-axis, and along the x-axis we have the crank angle. Now, in this diagram, two strokes are being shown. One is your compression stroke, and the other is your power or the expansion stroke. Is there? Now, during these two strokes, that is compression. In compression, what happens is the piston moves from the bottom dead center towards the top dead center. So, on the x-axis, if you can see that the point where your x and y-axis meet, this is your point BDC is there. That is bottom dead center. At this, the angle crank angle is 180 degree. Okay. Now, as the during the compression stroke, the piston starts to move from the bottom dead center towards the top dead center, the angle starts to decrease. So there is the graph. This division is made at 30 degree. Okay, duration. Okay, so at BDC the angle is 180 degree. Then it reaches 150 degree, 120 degree, 90 degree, 60 degree, 30 degree. So there are 30 degree divisions are there. Okay, and then after 30 degree it reaches the TDC, that is the top dead center, where the angle becomes 0 degree. So from this bottom dead center towards at the TDC, that is the top dead center, the compression stroke has been completed. Okay. Now this uh, during the compression stroke, you can see that the pressure, it is at L, that is atmospheric pressure. So at point L, it is almost atmospheric pressure, and as the piston starts to move upwards and the air fuel mixture inside starts to compress, the pressure inside the combustion chamber or the cylinder, it starts to increase gradually. Okay. Now, in between at point N, that is around 35 degrees before the top dead center, 35 degrees before the top dead center, during the compression stroke, the spark is ignited from the spark plug at point N, that is around 35 degrees before the top dead center, the spark is ignited. From N till M. Okay. So this is the period of ignition advance or ignition lag. That is the time taken between the spark ignition and the actual combustion start. From N to M, this period is known as the ignition advance or ignition lag. And normally, this duration is around 0.0015 seconds. Okay. So during N till M, you can see that still the pressure increase is taking place gradually. Now, as this top dead center is reached, from M, you will see that the graph, there is a steep increase in pressure. So this means now at point M, the actual combustion has started, and this combustion is like propagating throughout the cylinder. Okay. And whole of the fuel starts to burn. So this means from M to the maximum pressure reached, that is around 45 or 44 bar is there in a petrol engine. Okay. From M, this increase in pressure is very steep. Okay. And the maximum pressure reached is around 10 to 12 degrees after the top dead center. So when the piston has moved around 10 to 12 degrees after the top dead center, the maximum pressure point inside the combustion chamber is achieved. After the maximum pressure reached, the graph starts to decline, or this graph starts to decrease it slowly. Okay. Now this is the period of, so here you can see that the graph is not steep is there. So this graph is slowly decreasing. Now during this period, some reassociations between or some chemical reactions are still going on. Now the combustion is complete, but after the combustion, because the temperature inside is very high, so some reassociations or chemical reactions are still going on. Now, these chemical reactions are producing some heat. After the combustion has completed, these reassociations or chemical reactions, they are also producing some heat. So that is why this graph is not going down steeply, but it is reducing at a very gradual pace. So this phase is known as afterburning. Okay. So during this afterburning phase, some energy or some heat is being produced. Okay. So this is your expansion stroke, and this it completes itself when this reaches the piston reaches your bottom dead center. Okay. So this is how the phenomena of combustion it takes place inside a 4-stroke petrol engine. Now, if we see this description, now this combustion process is not here you can see that the spark is ignited at point N, and then from N to M, okay, there is some ignition lag or there is some delay in actual combustion that is taking place. Okay. Now this delay of combustion, it can be divided into two different stages. So first is your physical delay. Okay. In physical delay, what is happening is there is a when the spark is ignited, so the fuel that is in the direct vicinity or of the spark plug, so that fuel it produces a self-propagating nucleus. Okay, so that nucleus, the flame nucleus, is developed. Okay, and this delay is known as your ignition lag or the ignition advance. Okay, this is your physical delay. So in this diagram below, you can see that the first stage is where the spark is ignited, and you can see that the combustion is only in the near vicinity of the spark plug. So this blue region is there. So after that, layer by layer, this heat is propagated throughout the air fuel mixture inside the combustion chamber, and after certain seconds, you can see this flame is increasing, and after that the flame is increasing. So layer by layer, this flame it propagates throughout the combustion chamber. So second type of delay is your chemical delay. Now this when the self-propagating nucleus has been formed, now the time taken for this flame to reach throughout the combustion chamber. Okay. So all the fuel particles when they get combusted or they get burned, it takes time. So the spreading of this flame, it takes time. Okay. In the second diagram, you can see. So here we have time T1 is 12 milliseconds. Okay. So now the ignition has been, the spark has been ignited, and the first nucleus has been formed near the spark plug, and the flame is only, it's small in size. So at 15 milliseconds, the flame area is more. Okay. Then 18 milliseconds, 21 milliseconds. So time is there. So 33 milliseconds. So here now this combustion or this flame has propagated throughout the combustion chamber. So this means there is some time lag between when the spark is ignited and the combustion of whole of the fuel inside the combustion chamber takes place. So this delay is known as your ignition lag or ignition advance. So it occurs in two phases. Basically, it is your physical delay and is your chemical delay. Now, in the diagram here, you can see L, N, Q, M. Now, here the L, N, Q, M is your compression stroke. Okay. In this diagram, at point N, what is happening is the spark is ignited. So at N, spark is ignited, that is 35 degrees before the top dead center. So then the ignition lag or the ignition advance starts at this point, but no pressure rise is noticeable. So from N to M, you can see that the pressure rise is gradual. It is not immediate. Okay. So it is not noticeable at this point. So M is the point where the pressure starts to rise. From this point, the simple compression curve deviates from the combustion curve. So here you can see that this in this diagram at point N. So we have two curves here. One is this red curve and the other one is your this curve that goes steeply upwards. Now this upward curve is known as your combustion curve and this red curve is your simple compression curve. Now if suppose there is no fuel, okay, only air is in there, okay, and the compression stroke takes place and after that the expansion stroke takes place. So if there is no fuel burned, okay, so this steep increase in pressure will not be there. So this will the curve will follow this simple compression curve. But if the fuel is there and the fuel burns at point M, because the combustion starts at point M, actual combustion, so this pressure rise will be steep and it will reach a point of maximum pressure. Okay, so this is the difference between the two curves, that is your simple compression curve and the combustion curve is there. Now the time lag between the first ignition and the commencement of the main phase of the combustion is called your period of incubation, or it is also called the ignition lag or the ignition advance, and this time is normally around 0.0015 seconds. The maximum pressure is reached at about 12 degree after the top dead center. So here you can see that the peak of the pressure, it reaches around 10 to 12 degree after the top dead center. So this is your top dead center line. So 10 to 12 degrees after the top dead center, the maximum pressure curve is achieved. Even after the maximum pressure point, there are some chemical reassociations that take place and heat is generated during this period, and this phenomena is known as afterburning. So this is already I have explained that after the top maximum pressure is reached, this graph does not go down like steeply, but this graph follows a gradual decrease in the curve. This is because of the chemical reassociations or chemical reactions that are taking place even after the combustion is complete. So this is known as afterburning. Now this afterburning also produces heat. So this is how the pressure versus crank angle diagram for the combustion of fuel inside a petrol engine behaves. Now, after we have studied the pressure versus crank angle diagram for a four-stroke petrol engine. Now we move on to the four-stroke diesel engine. Now here again we have we are going to analyze the two strokes, that is your compression and the expansion or the power stroke. Again we have two graphs here. This your continuous line or black continuous line, this shows your the pressure variation during the compression and the expansion stroke, and then this is the dotted line. This shows the simple compression curve. So now again we are moving during the compression stroke, that the increase in pressure is gradual. Okay. Now at this point here, the ignition or the injection of the fuel from the nozzle, it starts. Okay. Now as the fuel starts to enter the combustion chamber, again the phenomena of your physical and chemical delay kicks in, where the first nucleus is developed and the flame front is developed. Okay. Now this time lag in the case of or the time advance in the case of diesel engine is around 0.001 second. Okay. Now this combustion inside the diesel engine, four-stroke diesel engine, is divided in 4 stages. This first stage, that is, you can see these vertical dotted lines are there. The first stage is known as your ignition lag. Second stage is known your period of uncontrolled combustion. Third phase is your the period of controlled combustion, and the fourth phase is your the phase of afterburning. Okay. So now in diesel engines, what we do is we don't have a spark plug, but we have a fuel injector. Now at this point, you can see the fuel has been injected, and from this point till this line, dotted line, the first flame front has been developed. Okay, or the self-propagating flame is developed, and during this phase, the amount of fuel that has been entered, it will burn abruptly at up till point 2. Okay, so this point, this phase 2 is the phase of period of uncontrolled combustion. That is, all the fuel that has entered the combustion chamber, it will start to burn. After that, how, at what point the fuel injection has to stop, that is controlled manually or electronically. Okay, with the help manually with the help of say cam, or electronically with the help of ECU there. So ECU decides, or the cam, it decides that up till what point the fuel injection will go on inside the combustion chamber. So this phase 3 is your the period of controlled combustion. Okay, so that is why it is known as controlled combustion. So up till what point the fuel will be injected inside, and the fuel that will be injected inside will burn, and this period or this peak will be reached. Now this peak is your maximum pressure peak. So you can see that the maximum pressure inside the diesel engine reaches is around 80 bar. So it was around 44 bar in a petrol engine, but inside a diesel engine it is around 80 bar. So double pressure is there inside a diesel engine. So after the phase of, so again, you can see that the top dead center is here. So maximum pressure point, it reaches around 10 to 12 degrees after the top dead center. After that, the phase of fourth phase is your afterburning. So again, chemical reassociations takes place inside the combustion chamber after the combustion has completed. Now these reassociations, they produce heat. So that is why this is gradual decrease in pressure inside the combustion chamber during the fourth phase, that is the afterburning phase. So in this, you can see that the whole combustion inside a diesel engine has been divided into 4 stages. The first stage is your ignition advance stage. Second stage is your where the fuel that has been injected till this point, it will burn. So this is your period of uncontrolled combustion. So all the fuel that has entered, it will burn. You cannot control the combustion. But after this period, so at what time the combustion will stop, that is decided by the manual means or by the electronic means. So that is why this is your period of controlled combustion. There, during this period of uncontrolled and controlled combustion, the peak, that is the maximum pressure point, is attained. And after the period of controlled combustion, where the fuel injection stops, okay, the afterburning starts. So this is the phenomena of combustion that takes place inside a 4-stroke diesel engine. Okay, after the pressure versus crank angle diagram for the 4-stroke diesel engine, we move on to the various phenomena that are there for the mixing of the air and fuel inside the combustion chamber. Now, this mixing of air fuel is very essential to form a homogeneous mixture of air and fuel inside the combustion chamber, so that the complete combustion of fuel takes place. So the first phenomena that is required is the turbulence. So turbulence is directly associated with the Reynolds number. So higher the Reynolds number, so in the case of fluid flow, if the Reynolds number is above say 4000, okay, so that flow is known as a turbulent flow. In turbulent flow, what happens is different layers of the fluid, they intermix with each other. Okay, so this turbulence plays a very important role in the combustion phenomena, and it helps in the intermixing it intensifies the intermixing of the air and fuel inside the combustion chamber, and even during the combustion process, when the flame has been first flame front has been developed inside the combustion chamber. So this turbulent motion, it helps in carrying this flame to the various parts of the combustion chamber, so that the fuel that is present in each and every corner or each and every place inside the combustion chamber, it gets heated up and the combustion takes place. So it also helps in intensifying the process of heat transfer, and helps in burning the unburnt portions of the flame inside the combustion chamber. Okay, so next type of motion or phenomena is your swirl motion. Yeah. So swirl is the circulatory motion that is provided to the air or the air fuel mixture that enters the combustion chamber from the inlet manifold. So this is achieved by designing or constructing the intake system in such a way that the air or air fuel mixture that is entering inside the combustion chamber, it gets a tangential component. Okay, now this is done by shaping the contours or shaping the your inlet valve in such a way that the air that is entering, it gets a tangential component. Okay. Now this tangential component helps to achieve this circular motion of air. Now this circular motion of air, it helps in producing a swirl motion that achieves the turbulence inside the combustion chamber, and it also helps in intermixing of the air fuel mixture and helps in forming the homogeneous mixture. Next type of phenomena is your squish. Now, when the piston is moving in the upward direction, the compression is taking place, and the air or the air fuel mixture that is at the edges of the piston, it is pushed in the inward direction. जो edges पे रहते हैं, the edges, air or air fuel mixture that is at the edge, it is pushed radially inwards. Now, this motion from the outer periphery of the combustion chamber towards the center of the combustion chamber, this motion is known as the squish. Okay. Now this radially inward motion, what it causes, it also helps in intermixing of the air and fuel inside the, and to achieve the turbulence inside the combustion chamber during the compression stroke. Now maximum squish velocity, it occurs about 10 degrees before the top dead center during the compression stroke. And the fourth phenomena is your tumble. Now this squish motion, that is the air that is going inwards radially. Now when two opposite fronts, they meet each other at the center, so one circulatory motion is developed at the center. Now this circulatory motion is known as your tumble motion. Now this tumble motion also helps in intermixing or creating a homogeneous mixture of the air fuel inside the combustion chamber. So all these phenomena of that is your turbulence, swirl, squish and tumble, it helps in creating a homogeneous mixture of air fuel, and also help in even propagation of flame during the combustion chamber, during the combustion of fuel inside the combustion chamber. Okay, next is the process of dissociation is there. Okay. Now dissociation, as the term in itself explains, it is the disintegration of the products of combustion. जो मेरे products of the products of combustion, that is carbon dioxide and water are there, they disintegrate at higher temperatures. Now during this higher, because we know that the temperature inside the combustion chamber, it reaches around 2000 degrees centigrade during the combustion process. Now at such high temperature, this carbon dioxide at 1000 degrees centigrade, it disintegrates into carbon monoxide and oxygen. And also water, H2O, at 1300 degrees centigrade, it disintegrates into hydrogen and oxygen. Now this disintegration, what it does is it absorbs heat rather than it produces heat, it absorbs heat. So this means this dissociation, it reduces the thermal efficiency of the engine. Okay. So this means if you see there are three types of fuel mixtures are there. There is lean mixture. Lean mixture is when there is less fuel and more oxygen is there, more air is there. Then is your chemically correct mixture is there. In chemically correct mixture, 50% fuel and 50% air is there. And then the third type of mixture is your rich mixture. Rich mixture, in rich mixture, we have greater percentage of fuel and less percentage of what this air is there. So there are three types of fuel mixtures are there. Now in lean mixture, where fuel is less and air is more, the temperature produced is less. So this phenomena of dissociation is very low or not available in the when there is lean mixtures. Okay. Now in chemically correct mixture, where 50% is your fuel particles and same 50% is your air particles. So this means complete combustion of fuel will take place in chemically correct mixture and maximum heat will be produced or maximum temperature will be achieved during the chemically correct mixture. So this means maximum dissociation takes place in a chemically correct mixture. And then this richer mixture, in this richer mixture also dissociation is prevented because there is more fuel and less oxygen is there. So this means incomplete combustion of fuel will take place, and because of the presence of carbon monoxide and oxygen, because of this incomplete combustion. So dissociation also is avoided in richer mixture. So maximum dissociation it takes place in the chemically correct mixture, and some dissociation is possible in lean mixture, okay, but it is prevented in the richer mixture because of incomplete combustion of fuel and the product and the presence of carbon monoxide. After dissociation, the phenomena is of your auto ignition. Okay. Now, as the during the combustion, okay, during the compression, all right, the fuel and air, in the case of petrol engine, so air and fuel is there present inside. Okay. Now, in that, when the compression is taking place, okay, now this compression results in increase in temperature. Okay. So this increase in temperature, what it does is it, in the presence of the spark or the flame, sometimes the self-propagation flame is produced by itself because of the compression process. The heat inside is the temperature inside the combustion chamber, it increases, and before the spark is ignited, the temperature reaches certain limit that in the absence of flame, the fuel starts to ignite. Now, this type of self-ignition in the absence of flame is known as auto-ignition. And the temperature at which this self-ignition takes place is known as self-ignition temperature. The pressure and temperature, it increases abruptly during this auto-ignition because of or the sudden release of chemical energy. And this auto-ignition is the cause of knocking or detonation inside the IC engine. So in the absence of any flame or in the absence of spark, the spark has not been ignited. Okay. And because of the compression process, the heat inside the combustion chamber, it reaches the self ignition temperature, and the various flame fronts are formed. Okay. So these various flame fronts, they start to ignite. Okay. And when they collide with each other, they result in knocking or detonation. Okay. Now these various flame fronts, when they are developed, okay, so these flame fronts, when they collide with each other, they cause a lot of sound, and with that loud sound, metallic sound, there are vibrations. Okay, now these vibrations and sound, they are very damaging for the uh, various parts of the engine. Now after auto ignition, there is pre-ignition is there. Now in this case also, what happens is the from the previous ignition or the deposition of carbon on the various parts of the combustion chamber, like on the edges of the uh, piston, okay, and on the edges or the electrodes of the spark plug, okay, or the you can say the edges of the your fuel injector in the case of a diesel engine. Now those edges from the last combustion or the heat, they might be glowing red hot. Okay, so they are red hot, and then there is carbon deposits. Those carbon deposits, they also glow, uh, and they are red hot. Okay, so the homogeneous mixture, okay, when it comes in contact with these glowing surfaces or hot surfaces, in the absence of the spark, these, what they do is they produce the ignition process, or they produce the, or they ignite the fuel in the absence of spark, and a flame front starts to form. Now this flame front from that is caused from these glowing surfaces or hot surfaces is known as pre-ignition. So again, this pre-ignition is the cause of detonation or knocking inside a IC engine. Okay. So pre-ignition is initiated by some overheated projecting parts such as spark plug electrodes, exhaust valve head, metal corners in the combustion chamber, carbon deposits, or protruding cylinder head or gasket rim inside the combustion chamber. So there is difference between pre-ignition and auto-ignition. Okay, auto-ignition is it takes the ignition takes place during the compression stroke without the presence of the flame. Pre-ignition is the again the ignition in the absence of the flame or the spark, but from the glowing surfaces or the hot surfaces. So this is the difference between auto ignition and pre-ignition. So after pre-ignition, the next phenomena is what is knocking. Now before we study knocking, so suppose this there are two diagrams here. The first diagram A is of the combustion chamber. Okay. Now in this combustion chamber, A is where the fuel injector or the spark plug is installed, and D is the farther, or you can see this is the D is the point where your piston head is. Okay. And in between A and D, you can see these curves here. These are your various layers of fuel. Okay. And then on in diagram B, you can see that the same is your pressure versus crank angle diagram there. So where the compression takes place, ignition is ignited, okay, and then the maximum pressure point is reached, and after that, afterburning takes place. Now this is for a normal combustion. Okay. Now the flame travels from point A. A is the point where the spark plug is installed or the fuel injector is installed. So flame front jo mera hai, it moves in layers. So first layer gets ignited, it passes the heat to the next layer gets heated, it passes the heat to the next layer. Okay. Now what happens is when the first layer ignites, it produces a pressure wave in the opposite direction. When the second layer ignites, it produces a pressure again in the opposite direction towards the next layer. So this last layer, if you see B dash D, this is the last layer that is on the piston head is there. So this is the last layer. So this last layer is continuously under increasing pressure from the combustion of the previous layers. Now, if the final temperature before the actual flame front reaches this last fuel layer B dash, it is less than the auto ignition temperature of the fuel, then the combustion will take place normally, smoothly, and the curve will be smooth. So this is normal propagation of flame. Now, if there is some abnormal combustion takes place in the phenomena of knocking, so what happens is, again from A to D, the flame front is advancing from A towards D. Okay. Now this last layer, that is C dash D. Now in this, what happens is, because of these layers, they are combusting, they are producing pressure on this last layer. And if this last layer, the temperature and pressure, it reaches the auto ignition temperature. So what will happen? This last layer will burn before the flame has reached this layer. Okay. So in this diagram on the right hand side, you can see that one is the flame front that is normally propagating throughout the cylinder. And because of this pressure, the last layer, that is 2, another flame front is produced because of auto ignition. So there are 2 flame fronts now. And in some cases, multiple flame fronts are developed. Now, when these multiple flame fronts, they collide with each other, they produce a lot of sound, metallic sound is there. Okay. And a lot of vibrations are produced. Now you can see in this graph, in the previous graph, this graph was smooth. Now in this graph, there is fluctuation. Now this fluctuation is knocking. So a lot of vibrations are produced, and these vibrations are very damaging for the various parts of the engine. So here you can see that because of knocking, what type of damage can be caused. So here there is this damage is caused to the piston. Again, this piston edge is damaged. This cylinder, you can see this, there is damage to the cylinder lining. Okay, again, this is damage to the cylinder head. So this is the ill effects of knocking.